Western Ontario. He'll be speaking on personalized medicine today and tomorrow. So I think that will be a very interesting talk for those of you that can attend in person, and it will also be webcast. And lastly, we offer a number of workshops. The first one coming up will be next month, March 26th to the 28th, and it is entitled eHealth Information Security. So if you're interested in attending that workshop, the registration is open now, so please go to our website, hi.uwaterloo.ca, and you can learn about the workshops that we're holding both in March and in April. So without any further ado, Maher, will you introduce our speaker?
Good afternoon and welcome everyone. It is my pleasure to introduce our guest speaker today. Beth Jewkes is a professor and chair of the Department of Management Sciences at the University of Waterloo. Her research interests focus on stochastic models of manufacturing and surface systems, with a more recent focus on the use of operation research in healthcare systems. Today, Professor Jewkes will talk about why shift scheduling for emergency room triage nurses is challenging, lessons from operation research. This talk stems from some work done with the Grand River Hospital while seeking to reduce the wait time in emergency room. Welcome, Beth.
Thank you, Mahar, and thank you. Well, it's a pleasure to be here, and it's nice to see some familiar faces and also some faces I haven't seen for a while. What I'm going to talk about today is less research-oriented, but more oriented towards some experiences that a group of students and I went through last summer as we studied the emergency room operations at the Grand River Hospital, and how some basic tools of operations research, 3 of them in fact, were tried out, and things that we learned in trying to use some fairly straightforward, simple operations research methodologies to the question of scheduling triage nurses in the ER. For those of you that have an operations research background, this will be very simple applications of operations research. But what I found really useful in this study was the fact that it brings to bear some analytical modeling to a problem setting that the individuals in the healthcare area may be less familiar with than those of us in the operations research area. As a little background, most of you are probably quite aware of the fact that ER waiting times have become a very hot issue in the last decade and a big concern. And of Ontario's population, 1 in 5 of us makes a visit to the ER each year, and many of us have experienced, especially if you go in the middle of the night with a child that is having an asthma attack, you really want to see that you get fast care for the ones you love. Sometimes, though, especially if the condition that we come in as a patient is not highly severe, we may experience long waiting times. In some cases, potentially up to several hours. And recently, as recent as October last year, the provincial government has added ER wait times to a list of other wait times that are being tracked by the ministry. And specifically, the kinds of wait times they're concerned about in the ER area have to do with ambulance offload time, which is another area I'm quite interested in. I've got a grad student actually doing some research in this. Time to physician assessment, which is the time from when someone comes in off the ambulance or off the street and has received triage and is registered and so forth until a physician actually sees them. Time to admission if they're brought into the hospital, ER length of stay, and the number of patients in the ER. So these are metrics that the provincial government is going to start tracking, and they're developing some new information systems to start monitoring these metrics. And in talking to the head of the ER department at Grand River, implementing these information systems is going to be a challenge. On the other hand, they look forward to being able to track, benchmark their performance and track it over time. So this project, what I'm going to describe to you, is actually undertaken as a result of a simulation course that I taught last summer. 3 of the students in the course did a study of the ER, and we were kind enough to be allowed into the ER by its clinical director, Bruce Adkins, and he was just a wonderful host to these students and basically gave us free rein. Well, not quite free rein. We weren't allowed into certain areas where the patients were, but essentially free rein access to the data and to interview the triage nurses and to understand in greater detail how the system operated. So thanks to all of them for allowing us to engage in this. So the basic process here, if you've been into the ER, you know the first thing that you do when you come in. Hopefully you didn't experience this route into ER. You're walking in or you're driven in. You come in and you self-register, write your name down on a piece of paper. And there are 4 triage offices or stations on the right-hand side where there are 1 or more triage nurses and also staff who help with the admissions process or the registration process. Once you're through the triage process, the nurse will assign an acuity level, 1 through 5, where an acuity level of 1 is basically called resuscitation. This is very severe, and you're rushed right through to another area for care. And those of us that go in with less severe problems, level 5, we may wait a little while until we actually see a physician after going through triage. We're not going to focus on the stages after triage, although that is also a fairly complicated area that the hospital is trying to reorganize to streamline the flow. What we're going to focus on today is this process of the patients arriving and this whole process of how triage takes place. This is a diagram, and my apologies, you can't really see in detail what's going on, but this is a flow chart condensed of what the hospital actually has on record as to what the processes are in the ER. Thank you. I won't spend any more time on this. It's just to say that it's a fairly complex process that patients go through when they're assessed, and decision-making at all stages by the triage nurse and by doctors and the other staff in the emergency. I made mention of the different levels of acuity when a patient comes in. The triage nurse basically, the triage is the process of prioritizing patients based on a fairly extensive list of symptoms that the patient may present, and they are assigned, as I said, level 1, which is the most severe. A patient may not have any pulse, so forth, so that's very severe, and they are generally whisked right through down to non-urgent care. Generally, most of the arrivals into emergency consist of the non-urgent, less urgent. Level 3 is urgent. They're monitored reasonably closely because they may progress into a level 4, or they may be stable at an urgent level. And there are many regulations within the ER that indicate how often you're supposed to check on a patient that is assigned each one of these levels to make sure that a patient's level of illness is not progressing or getting worse. In terms of patient processing, we're going to focus, as I said, on the triage process. A patient comes in, self-registers, indicates their name and the time that they've arrived, and they await in the triage waiting room, which is, as you go into the triage area, off to the right, opposite the triage, the 4 triage assessment areas. Fairly soon after, hopefully, the patient is assessed by the triage nurse. They're brought into one of the triage rooms. The nurse takes a variety of measures and assesses the acuity level and makes an assignment of the acuity level. And once the care that they need is basically determined, then the individual, another individual comes along to complete the registration process, which is to take the basic information of who the individual is and so forth. And then they would be transferred to either the rapid assessment area or other areas within the ER. After this, which is, again, we're not going to focus on this, is their primary assessment in the rapid assessment area, where if there's any initial directives or medical care that need to be taken place immediately, that's handled. And eventually, the patient assessment is completed and reassessed by the physician, and they may be admitted to the hospital, they may be kept for observation, or eventually they may be released. But as I said, our primary focus is on the triage. So as things are right now, there are 4 triage rooms. There are 1 triage nurse on at all times. Their shifts, they start 8-hour shifts at 7 a.m. and 8 hours thereafter. So basically there's 1 nurse on at all times, and then through the peak hours during the day, there's a second triage nurse available. The patients are prioritized, as I mentioned, by triage acuity level when they come in. And what we observed and what we were told was that the wait time to triage could be 15 minutes plus. It's not uncommon. And after school, when school lets out and so forth, there tends to be a real burst in activity. So the waiting time for triage can be an hour or more. And in some cases, we saw waits of longer than this and have experienced waits longer than that. So the question that was posed to us as part of this project was, could we help them figure out what to do with the triage process to try and reduce the waiting times? So as good engineers, the first thing that we did was to collect information about the system, study it in its setting to try and understand what actually happened, which is how we collected the flow charts of the decision processes. And the students visited the ER on numerous occasions to actually observe patients arriving and the triage nurses working with the patients and the registration process and so forth. And fortunately, we had quite a bit of data that the ER department had on hand with respect to the arrivals and the acuity levels of the patients coming to the ER room. So we had a fair bit of data in hand. What we didn't have was actually how long it took the triage nurses to complete the triage task. So one of the things that the students did was to collect a fair number of observations of how long the triage times took. And the average was about close to 9 minutes, and it varied from 3 or 4 minutes, and in some cases it was up to 18 or 20 minutes. And Bruce Adkins, as we discussed with him about this, thought that it was long. He'd like to get that time down. And I think there's evidence in our subsequent work that would indicate that the waiting times that they're experiencing are not surprising, either given the arrivals, the level of demand, or given the actual time it takes to do triage. Yes?
Nurses knew that they were being measured?
By the way, if we have questions during, if you get a microphone to the person.
Well, I'll repeat the question.
Okay.
The question was, did the nurses know that the students were watching them? And the answer was yes.
Sometimes they just tend to work faster.
Or slower. or slower. Actually, the students and I were introduced to all the nurses, so they were fully aware of what was going on. We did observe, this is the data that we got. We used it rather than questioning. We could go back and resample at another time, but this was the data that we got, and they were fully aware of what the students were doing.
And another one, like, so the purpose is just to...
We need to capture one.
Oh.
Because it's being webcast.
So the purpose is just to decrease the average time and not based on the acuity?
What we did at first in terms of this assessment was to take a fairly aggregate view of the process. We did not initially get into the specific wait times per level. It seemed that, based on our observation, that the nurses were quite able to expedite the severe cases. So this wasn't a huge concern. Those were taken care of quite well. The concern was how long the non-urgent cases were taking, the level 4 and level 5 were taking. So all of what I'm going to talk about now, it's not broken down by acuity level. It's done in the aggregate. But with the data that we do have, we could drill down another level. But everything we've done here is just based on the aggregate. So going back to the data, we had a look at the data from January to July of 2007 and looked at the arrivals as a function of the time of day. And we were told verbally that it's pretty quiet overnight, and then through the day, starting in the morning, the arrivals, this is midnight and approaching midnight at the other end of the scale. So what we're seeing here is come 9, 10 o'clock in the morning, you have a peak, and then after lunch, and you can see this is before dinner, and this is after dinner, what seems to be happening in terms of the arrival patterns. We also looked at the day-to-day comparison of arrivals, and it's actually remarkably similar. We did note that Friday night and Saturday night were a little bit more active in the ER through the wee hours of the morning, which I think is probably something else to be expected. So in looking at this data, we decided not to focus on a particular day because they seem to be pretty much all the same. We focused on a typical pattern during a day of arrivals, and thought that our analysis could carry over to pretty much any day based on this very strong similarity from day to day in terms of the average numbers of arrivals per hour. On average, there were about 156 arrivals over a daily period. The data that we collected in triage times indicated that there is quite a wide variability in the triage times, averaging, as I said, just shy of 9 minutes. But we can also see up here that there were some longer triage times in the data that ranged as high as 18 or 20 minutes. These must have been very difficult cases to assess. We left this in the data, assuming that it represented the real range of triage experiences that the nurses went through, although it does have, these data points here do have an impact of increasing the average a fair bit. So the results that we might get by excluding these data points, I think the overall results will be similar. But we left the high-end triage times in the data. So the first thing that we thought of doing was to say, okay, given their current arrival patterns and their current service times, if we were to do a fairly rough cut analysis of whether there was sufficient capacity, just at a daily level, was there evidence that there is an issue or a concern? And after having done that rough cut analysis, we saw, based on close to 9 minutes per patient, an average of 156 arrivals. Their 4 8-hour shifts should be sufficient in the aggregate to cover the requirements of the triage operations. Now, this is the 8-hour shift is in its aggregate. They're entitled, each nurse is entitled to 2 30-minute breaks in an 8-hour shift. So if we were to consider their overall utilization without breaks was 71% and roughly 80% including the breaks, which is not, in terms of industry norms, is not excessively high. In fact, they try to not plan for over 85% utilization. It allows for washroom breaks and interruptions that are unexpected. So it looked as if in the very aggregate there was sufficient capacity. Then we take the next step of drilling down. What about the time of day variation? So our first attempt at the nurse scheduling was to take into account the time of day variation in the arrival patterns. And for any of you that have done any operations research, you recognize that one of the first linear programming problems that you talk to students about when it comes to scheduling staff, it's a very classical linear programming problem that basically indicates or asks the question, how many staff should start at each hour, assuming a shift of 8 hours or 12 hours, in this case 8 hours, in order to provide sufficient staffing time to cover the requirements for each hour. It's a classical OR problem. So we have an objective function, and we have a series of constraints, one for each hour in the day, in order to try to ensure that there is sufficient capacity. So here's where I was going to ask you the question. I won't for now.
Thank you.
So the symbols and so forth aside, the linear programming formulation has a set of variables, in this case 24 variables, each indicating the number of nurses to start in a particular hour, hour 1 through 24. And we could, from the data, calculate the triage time that was needed. And we calculated that from the average number of arrivals by multiplying by the average triage time that was necessary. So we were able to come up with an Excel spreadsheet that listed by hour how much time on average was required. And then we can write our constraints here by saying, essentially, that in the first hour, 1 a.m. in the morning, those that are on shift are those that started 8 hours before, 7 hours before, and at the beginning of that hour. So we have a constraint per hour that essentially states who will be on shift, and the sum of those variables actually, I've just realized that my notation is a little bit off here. We have to adjust for the triage time that's available for each of those. My apologies. So there's an adjustment factor here of 8.8 minutes per. Several ways to formulate this. So we could solve this, and it was very straightforward. It's a very simple problem to solve. And what we did was we implemented it in Excel. Excel has in its analysis tool pack an optimization package solver that we used. And what we're able to do is, through this implementation, we're able to look at the solver came up with numerous alternate optimum solutions, and basically one could understand why. Is all of the solutions had a base case of 1 nurse on at all times. So if you've got 8-hour shifts, there are many ways you can have 1 nurse on at all times. So we basically said, okay, here's your base case. We'll use the shift scheduling that they're currently using to make sure there's 1 nurse on at all times. Then strict adherence to our constraints with respect to the time that was required led to a conclusion that they needed 5 nurse shifts rather than the current 4 that they had. And the difference, primary difference between what they were doing and what was recommended here by the optimization was that the optimization recognized the need for more staff later in the day than they currently had. We also recognized through the optimization, though, that we were assuming 8-hour shifts, and if we had allowed for something like a 4-hour shift, the solution that we might have gotten would to say certain combination of 8-hour shifts plus this extra piece. We need about 4 hours late in the day. So our optimization actually led to some indication that they didn't have enough staff to cover their current demand. 5 nurse shifts was difficult to justify in terms of salary. What we did look at then was to look at what would be the consequences of just using the 4 nurse shifts that they were currently using, and to see if we can demonstrate why they're having the challenges they're having. So if we did that, and we allowed some of the constraints in the optimization to be violated, that is to say there wasn't quite enough staff on in certain periods, what we found was that there were very short periods where the demand outstripped the supply. They didn't look like these periods were all that long, however. And the question still remained, why are they observing such long delays? So here's a couple of the Excel graphs that we produced. Along the x-axis is the time of day, hour 1. And please forgive this, this is actually, it starts at 0 here. This is a function of Excel. So this curve actually starts up here and should be contiguous and wrap around to the other end here. But this red line here indicates, it should be familiar looking, it's the amount of triage time needed. It basically follows the same pattern as the arrivals that we observed. And assuming that we have a nurse coming on at 7 a.m. and then 3 p.m. and 11 p.m. and 7 a.m., that's the cycle that they were using, and then an extra nurse coming on at 10, and allowing them another nurse to come on at 3. This is the 5th shift. We see that with breaks of 30 minutes every 4 hours, that's what these dips are all about, is the nurses taking breaks, that we have sufficient time available at all times, on average. Adjusting for 4 8-hour shifts with no breaks, we end up with a graph like this. So you can see where there are little areas of difficulty here and here late in the day. And if you add in the breaks, you can see where there's a bit of shortage here and shortage here. Now, we recognize that this dip here, that in reality, the nurses actually shuffle when they take their breaks. So this break here is programmed into the optimization. We could probably smooth this out by having the nurses basically shift times that they take their breaks. But this is roughly the current solution. So you can begin to see why there are some wait times. But the shortfall, if they were to smooth this out by adjusting the times that they take their breaks, so maybe smooth it a little bit here, maybe the waiting times might not be as long as we've been seeing. However, the spreadsheet model is a pretty good idea of shift coverage. It allows the staff to see the results of changing the shift start times. And if I can leave my PowerPoint presentation here and pull up the actual spreadsheet, I'm not going to show you the entire spreadsheet, but this is what the constraints in the linear program look like. And the decision variables are across here, so you can see start a nurse at 7 in the morning, 11 in the morning, 3 in the afternoon, and 11 at night. And that this is the resulting pattern of nurse availability versus the requirement. So we can play around with these things. This will run the optimization, but I can do things, for example, of saying, well, I don't like this. What if we brought the nurse on instead of 10, instead of 11, that we brought them on at 10. So that's the result. You can see that we get rid of the shortage here, but it brings this shortage on a bit earlier because the shift is 8 hours. This isn't surprising, but it's really nice to have a graphical representation that someone can actually play with the shift times to see what the consequences are. So it gives us a pretty good idea of coverage. We can reformulate the optimization model or actually just simply play with the spreadsheet to see what different solutions might bring about. So what's the problem? The problem is that this is a deterministic model. And for any of us that have had some background in queuing theory, you recognize that variations in arrival patterns and variations in service times get you. And the example that I always give to illustrate that is, for example, if we had one arrival exactly every 9 minutes, no variation, and triage time took 8.8 minutes, no variation, you would never have anyone waiting. But the fact is, the arrivals are highly variable, and as you saw, the triage times are also highly variable. So the next little lesson in OR, having gone past a fairly straightforward optimization, linear programming, is to say, okay, well, what does basic queuing theory tell us? And although you can imagine quite a number of complex queuing models, just looking at a very simple queuing model, an MG1 queuing model, this is where you have Markovian, reasonably random arrivals of customers, general service time for triage, and if we consider for now just one nurse, there's a very well-known mathematical formula that relates the service time, characteristics of the service time, and the arrival patterns to the waiting times. So the formula basically says if this is your average arrival rate, this is the second moment of the service time, which is a measure of variability. Your denominator has an expression in it that captures how busy the server or the nurse is. So the higher row varies between 0 and 1, the busier the nurse is, and the larger this ratio. The higher the variation in the service time, the larger the numerator, and the longer the wait. So that's the second lesson in operations research, a fairly straightforward one that we quantified somewhat by looking at the data. We looked at the data for arrivals, and although it's not a perfect fit to the MG1 model, where you have Markovian arrivals, it's not too bad. So we considered, you just look at this, you can see that the arrival patterns vary quite a bit. Now this is Monday between 10 and 11, so that over the consecutive number of weeks of data that we had, you can see that the average arrival on a week-by-week basis varied a tremendous amount. And not only that, the arrival times within a particular day are quite variable. So this is the variability in the arrival process we were concerned about. And you saw the variability in the triage time. So if we were to capture those things and put them into a very simple queuing model, which was to say, my apologies, this is on the horizontal axis, this is the number of arrivals per hour, assuming each of them takes 8.8 minutes on average, and we have a variance of about 20 minutes. You can substitute into the queuing expression, and we can see that as the number of arrivals per triage nurse increases, we start to see an increase in the expected waiting time. So as it turns out, if we're looking at the average situation that a triage nurse experiences, they're operating in around here. This is about 71% utilization. And if we take into account the breaks, they're operating about here. Why is that important? It's important for two reasons. One, well, several reasons. One is it starts to explain some of the waiting times that they're having. And two, they're approaching being so busy that this queue is, you know, if I plot at 7 arrivals per hour, this essentially becomes infinite pretty quickly. So they're operating in this area where the system is extremely sensitive to changes in arrivals or changes in service times. So queuing theory tells us that they're operating in a dangerous range. And this is where, again, I feel that some basic lessons in operations research brought to a very challenging problem can lead to some very useful insights. So the observations that we had, with 4 nurse shifts, triage is operating at roughly 80%. It's a critical operating point, as I was pointing out. Even small fluctuations in the actual arrival rate or service times in a particular day can cause fairly long waiting times to ensue. That queuing formula, I pointed out, assumes steady state. This system does not operate in steady state. So what does the operations research person do? They pull out the next lesson, which is, well, I'm not so great at looking at non-transient or non-stationary queuing problems. Some people or some researchers do have this as an expertise area. Well, the students were taking a course in discrete event simulation. So what we pulled out of our operations research tools was a simulation of the triage process that allowed us to capture the arrival process, the service process. As I said before, we didn't get into the acuity levels, but at an aggregate level, what we were able to do was to see how the existing triage schedule actually worked out on a typical Monday, which was typical of the rest of the week. And we could play with different shift patterns as well. It's a very challenging problem. So the simulation results with the current shift schedule show significant queuing late in the day. What we observed from the simulation, which my feeling is that it may overestimate the queuing time somewhat. But the wait times can approach 2 hours. A 5th shift would surely solve the problem, but I'm not sure that it's entirely necessary. Some additional help late in the day could make a significant impact. I think probably the reasons for that are fairly obvious at this point. Or alternately, reducing the triage times could have a large impact. So the questions that we might ask there are what tools or process changes, what assistance to the nursing staff could help the triage nurses with their tasks. Now, again, at this point, now this is where I was going to actually demo the simulation model. So this is the model that the students actually constructed. My apologies for the really small font size. These entities here represent the arrivals of different types of different kinds of patients. Level 1 acuity, level 2, 3, 4, and 5. These blocks here in the simulation act as a feeder to the rest of the simulation. The individuals come in, they note the time of their arrival. This is a a block in the simulation that represents queuing in the triage area. These are the 4 rooms. However, not all of them are filled at any one point in time. The staff down here, we have several triage nurses, and the simulation allows us to take advantage of 2 nurses or 3 or 4. Now, we may not use them all depending on the particular configuration of the simulation. So we're able to, in the simulation, embed shifts into this. So what's embedded in this simulation is the current, the 1 triage nurse on at all times and a second through the peak hours of the day. So those of you familiar with Simulate, I'm going to run this fairly slowly so you can see roughly what happens. The students set it up in such a way that these icons here and the icons that represent arrivals, actually they're animated so you can see them coming. The clock actually does capture the time of day where this is midnight, and it runs for 2400, runs up to midnight the night before. This represents the triage processes. These resources, the triage nurses essentially assist here, and depending on how many are on staff at a particular hour, the rooms will be occupied, either 1 or 2, with 1 or 2 triage nurses. This represents the registration process. Turns out that we could have more or less left the registration process out of the simulation, as it did not act as a bottleneck. So let me just run the simulation so you get to see, oops, what happens. Oh, it's running it too fast. I'm going to slow it down. So you can see the patients arriving into the registration area and moving into the triage rooms. You might see all of the triage rooms. It may look as if they're all active concurrently, but they are in fact restricted by the number of nurses that we have on shift. So it's 10 in the morning. We're doing okay. A little bit of waiting. This area here will begin to show the effects of queuing a little bit later in the day. I'll speed it up a little bit. Don't want to speed it up too fast because we'll miss afternoon. When you start to see patients dwelling, whoa, in there, they're waiting. And you can see this is late in the afternoon. And in this particular simulation, it was fairly busy. So that's what the simulation, I mean, this is a pretty animation, but it also, under the covers, can provide reports in terms of where the waiting times are as a function of the time of day. And what we concluded from the simulation, I didn't want to put up a big graph of results because, quite honestly, I think there's some validation that we still need to do to make sure that the simulation is in tune, really in tune with what's happening. Triage is really important. The first lesson that we learned is that scheduling based on the averages gives you a reasonably good idea of what resources you need, but it does not take into account variation. So the optimization model was great, gave us some initial insight, but it doesn't take into account the variation. The steady state queuing models that I showed you do emphasize the fact that if you're operating at high utilization rates, that the system's extremely sensitive to unexpected variations in the arrival process or in the service time process. That's OR lesson number 2. That comes from queuing theory. They do highlight the basic challenge. And the lesson that we learned from simulation, it's a great tool. We still need to, in fact, validate the model more closely so that it could be faithfully used to look at the impact of different shift patterns. But it has to be in the hands of someone with the domain knowledge to understand whether it's producing results that are reasonable. And if you want to experiment with different shift patterns, you have to know whether they're reasonable to use. One could, I was, a number of years ago in Calgary, I was familiar with a pattern called a split shift, where someone works 4 hours, they go home, and they come back 4 hours later. That may not be workable in this setting. It may be workable to bring someone in for a short period of time late in the day to help augment the current staffing levels. So that's what we learned in going through this. They're not complicated operations research lessons. These are very basic tools, but I do think that we can take advantage of these tools, bring them to bear on challenging, really challenging problems for an area that's really, really important to all of us. So that's it.
We have a chance to ask questions and comments. Just ask you to give a second to get the microphone to you when you have questions. And put your hand up ahead of time and we'll keep things moving.
Dominic.
You basically study the triaging problem, which is putting people in buckets.
Yes.
It seems to me that one of the significant problems, though, is the treatment problem. That is, fine, now I'm in a bucket, but I always have my broken arm.
Absolutely.
And
Yes.
It seems to me what you've done here, you could actually, there's more variability, I think, but you could actually take what you've done and extend it to that
Yes.
second part that wasn't shown on the slide.
Yes, actually, the students started to study this problem in the course of the summer, and we had a much larger simulation of the whole process. But what happened is they ran out of time in the course, and they had other things to do in the fall. So I lost my legs in terms of studying that problem. I would dearly love to go back and study the rest of it because the
We just learned that the microphone Don was using is bad, so
Oh.
take that out of service. So
okay.
You're next.
He has one more question.
Oh, okay. I'll pass the microphone to him.
Well, what I could do is give him my...
I get blowing Shirley's ear here. The other question has to do with demographics. In this area, and this is my experience with the health system, it's not obviously totally broad, thank God, I haven't noticed significant wait times, for instance, for things like cataract surgery or joint replacement. That is, you can have it when you need it. So I'm wondering about demographics in this. If you go into the city of Toronto where, like, I guess we're probably serving with Grand River Hospital something in the order of 300,000 or 400,000 people max. You go into the city of Toronto, I don't know how many any given hospital services, but I'm just wondering about the demographics and how that would impact your model.
The short answer is I don't know, but I'm quite interested. There's a much bigger picture here with respect to how hospitals divide up their services and the demographics, the aging population, and the fact that this is a growing community. And so those are what we were looking at was a very operational model. At a much higher strategic level, there are huge questions that I think operations research models could be used to explore the more strategic levels. But that's something I'd be quite interested in pursuing as well. That will take a fair bit of more aggregate study and knowledge. I'm just learning about all of these things. Bruce was very, very patient with me and the students in learning how the system worked. So I'm moving over from being a manufacturing person into healthcare. So a lot of the lessons apply, but it's very different, very different. Oh.
Yeah, the triage moments that took 18 minutes or so, I got two questions related to that. First of all, were they actually significant? Did they actually change the numbers significantly? In other words, create longer wait times at certain moments? And were there any features associated, like you could watch them and see that were characteristic of those long triage times?
That I would like to know, and I don't know. The students actually collected the data, and my suspicion is that there is some other explanation for those longer triage times, and I don't have them, although I think that we might have an explanation for that. But to answer your question, the reason I said that I think the queuing times estimated in the model might be long is because I do believe that those extreme points probably caused this 8.8 minutes to be a high estimate of the triage times, and that there is probably something else going on with those longer times. But I don't have a particular explanation as to what that was.
I happen to work at the project site, so I'm
Thank you.
very, very appreciative of any assistance in staffing the department. And I had just a couple of questions, and one really segues into the previous question was when looking at the differences in the triage time, whether any of the students had an opportunity to look at the interruptions because they are significant, and thinking that might have increased your average time, because the triage nurse isn't just triaging a patient. There are many other interruptions that would add then to that triage time. So I was just
Yes.
wondering whether that had been addressed. And the other question I just had was, we do have duplicate triage time from 11 in the morning to 2300, and I didn't quite see that in there.
Yes, it's there.
Okay.
Yeah.
So,
To 2300.
yes. So we have 4 triage shifts at 6 hours in length, but we have 2 triage nurses all the time from 11 to 23.
Okay.
So in adding additional time at the peak times, which start around 11 or 10 or 11 in the morning, plus, just as you say, after school closes or urgent care clinics close, those are some of the variables. Were you looking at that additional triage nurse as a third person in those hours?
No, actually, we were working with data that Bruce had given us last summer. And I think that what you've just told me is you may have added a shift or added some time that's not in these results. But what you've added then is just the piece that I was talking about that was missing.
Okay.
Yes, but to go back to the question of the triage nurses, the students did notice that the nurses were interrupted quite a bit because they were doing other things as well. And that if it were just pure triage time that they were recording, they thought it would be lower than the 8.8 minutes. So that these times included interruptions.
They did.
But
Okay.
we felt it was reasonable to put the interruptions in because in fact, these interruptions were causing longer wait times. The interruptions were not helping for those in the waiting area be processed. So if we were to, strip out those interruptions, assuming that they didn't occur, I'm quite sure the results would improve quite a bit.
I have a question, and my question is there a wait time that hospitals are striving to? You mentioned 8.8 here, but what would they want to, or is there a standard?
The guidelines, the ministry guidelines are that people should be triaged within 15 minutes of arrival. And then a triage time, on average, you should be able to do it at 5. 5 minutes is what the ultimate of what we strive for. Some take a little bit longer, some take a little bit less. So if the average is 8.8, we have a way to go then.
But as I said, those do include interruptions. So I don't have a good feel for how much of that 8.8 is interruptions.
So I'm just wondering if we address the right, if we were able to take those interruptions out, whether that would have made a huge difference
It
to
would.
your...
It would, and the reason I say that is when I presented the graph that kind of showed the utilization rate of the triage nurses, it was just at a point where if there was any more pressure in terms of arrivals, that the wait times would start to skyrocket. If you move yourself back down that curve, you're in a much more stable situation. So I would say yes, it would have a big impact.
I have a couple of questions about what you were saying. First off, is the data being collected on an ongoing basis at all? And I suspect not, if it was a special project of students to go down and monitor. Secondly, is that data collection part of the ministry requirements for publishing? Like there's surgical wait times and a few other things that are supposed to be published on the hospital websites, but are triage wait times involved in that, or is it just emergency total aggregates, or do you know the numbers?
I'm not sure of how the...
We're in the information collection business.
Yeah, that's the...
We love questions like this.
Yes.
My understanding is the total wait times are recorded. I don't think you could find anywhere triage wait times.
I don't...
It's certainly
I don't
not
know.
broken out like that.
That's why the students went to collect the data by hand, because we didn't know. Although the staff had a really good idea of what it should be, or had a good sense of it. But for the purposes of the simulation, we wanted to get a feel for what the variability was.
Sounds like the students need a little extra tick box that says this was an interruption for 3 minutes as
Absolutely. Absolutely. Another example of that was more or less like this, in a manufacturing setting, collecting cycle time, a person doing a welding task. I graphed the task time, and it ended up being bimodal. Well, I discovered that the bump on the end was not a normal part of the process. It was, in fact, a separate thing where there was problems. And so we ended up taking that out. And perhaps the long triage times we observed are similar. So there are lots of things that perhaps could be modified about this.
My general experience in this sort of thing, and I'm no statistician, that's for sure, is that you get 2 or 3 answers, you also get 10 or 15 more questions.
Absolutely. Yeah.
I'd just like to ask a couple of questions. First of all, to make you more comfortable, we could move some heavy equipment into the emerge department. There's also a movement, by the way, to stop using the term emerge department. And the short form doesn't play well these days, so anyway, you have to figure that one out. What I'd like to know is first of all, did people capture any information on what the result of the triage was? In other words, which category they were triaged in? So you have that information. Yes. So we could relate the wait times to the level anyway.
What the data that we have is the arrival time of the individual, time of day we have the date, and we have the acuity level. And then we have some other subsequent information about what happened to the patient. But we used primarily the arrival time, time of day, day of week. And we didn't actually get into the acuity level. Our observation was that the nurses were really good at getting the level 1s and level 2s just right through. And that the waiting times were more common for the level 4 and level 5 patients.
It'd be interesting to see the correlation there. In other words, I mean, in some sense, very long wait times associated with the most acute patients would be an issue.
We don't have any of that. We don't have the wait times. We have the arrival times.
No, the triage time is what I mean by
right.
Yeah, just the triage time. See what I'm getting at?
Yes, yes. That's something we didn't look at, but
I mean,
it would be very straightforward to do.
If you have that data, it might be interesting to look at that. Because if you know which category they ended up in and you know what the triage time was, you've got an interesting piece of information.
That would be about a 5-minute work.
Yeah, it'd be interesting just to see that. The reason I asked the question is that at the time the supervisor was brought into Grand River Hospital, there was a real push on related to changing the way in which patients were handled in the emergency room, and that was to deal with, one of the strategies was to deal with the simple patients first. In other words, get rid of the easy ones, as probably the algorithm that was used. And you had just indicated that it seemed the simple ones were dealt with pretty quickly, but what we don't know is how they handled them after the triage process.
And that aspect of the operation, like I said, the students, I kind of ran out of my legs there, but that's a very complex process, and I do know, having discussed with staff at the hospital, that they were looking at reorganizing how the post-triage was being done. They were looking at considering something such as a registered nurse to potentially handle some of the things that a doctor would have normally done for the level 4, level 5 patients, and thereby express, deal with those patients much more quickly. There were a number of other alternatives being considered in the reorganization. So that would be to deal with the simpler ones quicker.
Yeah, that seemed to be something that was tried at another emergency room. And what I was curious about is how models like this could validate that strategy overall.
Very easily.
Very easily.
To develop the simulation model itself, it would take maybe half an hour to put in an individual to expedite the level 4 and level 5 arrivals. It would be very easy to do.
Okay. The only other comment I wanted to make is we've had Mike Carter speak here before, good friend of all of ours, and he has had an enormous effect, particularly in the Toronto area, on the hospitals, saving OR time, saving OR staff, all kinds of things. So when you say this stuff, even you call it the simple stuff, can make a difference. What he's shown is an enormous difference with his students. He claims to have about 100 students in the system right now, and to have had a significant effect on things like surgical times and number of staff and things like that. So thank you very much. Any other questions? Good. Well, thank you, Beth, very much.